Minnesota. I'm going to give a presentation called Beyond the Classroom, Heterogeneous Catalysis 101 with Dr. Omar Abdelrahman, and we'll be switching back and forth on different topics. This is intended to be an introductory short presentation on general topics in heterogeneous catalysis. But first, let me start with a safety moment. A common issue for academics and writers in general is carpal tunnel syndrome, or wrist injury. That's very commonly obtained from sitting incorrectly, using the wrong posture, but also the way your hand interacts with a mouse. I've had this occur several times, and now you can sense kind of a pain in your wrist, and you can change the way you're sitting, change the way your mouse. But also, the other thing to look for is your shoulder and back position. That can really affect the way your wrist rests relative to the mouse. It's a very important issue, and it's very common, and it can be a lifelong issue if you don't take care of it. All right, so for an outline for the presentation, we've split this into 4 parts. The first one about catalyst types, applications, and kinetics, after which we'll take a break for questions. Part 2, catalyst characterization on titrating active sites and surface area, after which we'll take questions. And then we'll end with advanced concepts, and then eventually real catalyst systems before ending. So let me go right to the first part of the presentation on catalyst mechanisms and kinetics. The phrase heterogeneous catalysis, it comes about from a very simple concept, which is that our reactant material is usually a fluid of some kind, liquid or gas, and we want to react it over a second phase. The heterogeneous catalyst is frequently a solid. So this fluid-solid combination is the most common variation of this, and it's usually done in something like a mixed tank or a straight tube flow reactor system. Now this introduces a lot of complexity in that you have chemicals moving from one phase to another, but it has a significant benefit that you don't have to separate out your catalyst from the reactant or product chemicals, which is very useful for process chemistry. But the question becomes, how do you introduce active sites for chemistry into a second phase? And that has to do with solid structures. In this case, porous materials like you see at the top, where you can introduce active sites such as a Bronsted acid site introduced with aluminum, or you can do other structures such as a foam monolith support you see on the bottom with supported metals such as platinum, rhodium, ruthenium, of many other different types. Now for any active site, no matter what it is, your goal is to create catalytic turnover. So you'll have some sort of catalyst surface where molecule A can adsorb from your fluid phase, probably into your solid phase to form A star. On the surface, the reaction proceeds to go from A star to B star, and then B star can desorb and you recover your catalyst surface, and that cycle can continue. Ultimately, the overall goal is that you can, if you look at the Gibbs free energy diagram on the right, and the reaction coordinate between A and B, you don't change the overall thermodynamics going from A to B, but what you are changing is the transition state energy between the reactant A and B. So you can see that once you form surface species A star and B star, you're at lower energy overall. So the question is, how do we describe this rate enhancement? And there are 3 general classes of describing catalytic rates. The first one being a power law, where we describe a rate just as literally a power rate expression with some parameter K, and then dependency on the catalyst surface site concentration S, and our reactants and products A and B to some power. And these are just usually fitted parameters. This is usually done when you're evaluating catalysts, and it can be very powerful for model development, but there's not a lot of insight into the chemistry. The next level is called Langmuir-Henshelwood-Haugen-Watson kinetics, where we assume a mechanism and we can develop a rate expression that has some relationship to a proposed mechanism. The third level is called microkinetics, or Lanny Schmidt would always call it detailed chemistry, where we write out the kinetics of every single elementary step, and then we solve it numerically, and we don't make any assumptions about the mechanisms. So if we think about how we're going to describe a system like this, the first thing that has to happen is a reactant has to go from a fluid phase to a solid. And to do that, a molecule at a significant distance from a surface will have negligible interaction energy, and as it gets closer, it'll eventually physisorb into the well you can see on the left. As it gets closer, it can eventually chemisorb with the surface to form a low energy state. Now at any time, we can measure the concentration in the fluid just by experiment, but we don't know the concentration on a surface. So what we need to know is understand some relationship between the distribution of molecules on a surface and in the fluid phase. So we need to know at equilibrium, what is the relationship between the surface and the bulk fluid phase. There are many ways that the two species can relate, and the simplest one is the Langmuir isotherm, where at 0 bulk phase pressure, we have 0 surface coverage, the coverage being a fraction between 0 and 1. 0 is a completely clean surface, 1 being a completely covered surface with one monolayer of species. And from the Langmuir isotherm, you can see the math described at the bottom. We can describe the fraction of surface species covered with species A. Now this gets more complicated in a reacting system because we have multiple species adsorbing at the same time, in which case we have the issue of having open sites covered with A and sites covered with B, and we can extend the Langmuir isotherm to describe the fraction of sites covered with species A as a function of the pressure of A and pressure of B and the associated thermodynamic coefficients as you see in the top left. And this can go to hundreds of species, as you see in the bottom, just by extending and knowing the thermodynamics and the partial pressures of any species. Now what's happening as you change these parameters, if you look on the right, the denominator, you have a 1 plus a term for species A and a term for species B. And as the relative ratios of those terms change, you can actually switch between a surface that has very low coverage, is mostly open. As KAPA gets large, you can have a surface dominated with species A, and as KBPB gets large compared to the other terms, you can have a surface that's dominated by surface B. Now this is very important for the reaction and the kinetics because that can control the rate of reaction based on what's on the catalyst surface. So let me take you to the second level of description. This is the Langmuir-Henschelwood-Haugen-Watson kinetics description of a catalytic reaction. In this case, we start on the left with the reaction mechanism, and we just write the reactions for each possible step that can happen. The first one being the adsorption of species A, which we'll say is equilibrated. Then on the surface, the surface species A star can react to form surface species B star. And then in the third step, surface species B star can desorb to give you gas phase or fluid phase species B. And altogether, we end up with an overall reaction of A goes to B. Now, by this approach, we have to make some assumption about what's controlling the rate of reaction, or what is the slowest step. And one possible option is to say that the surface reaction is rate controlling or extremely slow compared to everything else. In which case, we can say that the overall rate is just the rate of the second reaction, the slow reaction. And we can write the rate expression as the second reaction rate coefficient, K2, multiplied by the fraction of surface species covered with species A, which is what you see right on the top right above my cursor, K2 times theta A. Now this is useful, but not entirely useful because we can't measure theta A experimentally. We need to relate the surface coverage, theta A, back to some quantity we can measure, which would be the concentration or partial pressures. So if we then substitute in our Langmuir isotherm expression for theta A, we end up with a rate expression on the bottom with a numerator and denominator that's somewhat complex. Now we can interpret that rate expression by looking at experiment. If we take that rate expression, we can imagine three extreme scenarios. If you look at the top, if our surface is relatively open, very few sites are covered with A and B, then it turns out that the denominator term 1 is large compared to the other denominator terms. And we can reduce our complex rate expression to just K2 times capital Ka times A, which means our rate will be first order in reaction rate A. If we change the thermodynamics of our adsorbed intermediate species, A star and B star, you can see for the red line here that A star has very low in energy, and you'll end up with an A-dominated surface. If that's the case, if you look at the rate expression for the A-dominated surface, the Ka concentration term will be large, and they'll cancel with the numerator, and you'll end up with a rate that's just proportional to the K2 rate constant. It'll actually be zero order in the reaction concentration of A. The third option would be if you have a surface species that's covered in B, in which case B star is very low in energy, and your surface becomes covered completely in your product surface species B. And then if that term in the denominator is large, you'll actually form a complex combination of parameters of rate coefficients and thermodynamic coefficients. It'll be first order in the reactant and inversely proportional in the product B. So we say that this reaction would be product inhibited. And so knowing these different types of rate expressions and comparing with experiment allows you to get some idea of what's happening on the catalyst surface and what's controlling your overall system. Now, the third level that we can go to in reaction kinetics is to not make any assumptions. In the last example, we picked one of the reactions as being the slow step. But it's possible you could just write every single elementary step and then determine the rate and coefficients and thermodynamics of every single step, and then solve each of these numerically at the same time, and then evaluate how the overall system performs without any assumptions about what's fast or what's slow. This is a classic example of ethylene hydrogenation, where you adsorb ethylene on the surface, you adsorb hydrogen on the surface, then you hydrogenate to make ethane. And all the steps add together, as you can see in the overall reaction. Now, what's beneficial about this is that because you're not making any assumptions, the emergent kinetic pathway emerges from the complexity of the model. The problem being, for every single step, you have multiple parameters you need, and without high confidence in any of the parameters, you can't trust the output of the model. So there's a benefit and a drawback to this approach.
You ready?
Yep, you can go ahead.
Okay. So I'll be talking about some of the characterization techniques we apply in heterogeneous catalysis, which help us understand the catalysts that we're employing for any of the various chemistries we could be interested in. So kind of based on the questions we were just hearing, so this is commonly what we try and do when we're evaluating a heterogeneous catalyst. We have a packed bed reactor, as you can see here in the top right, which is just a tube, and then it's a flow system. In goes your reactant, out comes your product. And we have a small catalyst bed that we put there, and we keep it small enough such that the conversion is less than about 5%. So what it does, it's a differential reactor, and what that allows us to do is simplify the math so that when we're trying to estimate a rate of reaction over this catalyst, all we have to do is take the molar flow rate of the product and divide it by the catalyst mass. And so that gives us a rate on a mass normalized basis. However, different catalysts will show different rates of reaction even though we normalize them by the mass of catalyst that was used. And the reason for that is they can have different active site densities. All that means is I can have a supported metal catalyst. If I put 1 weight% platinum on my catalyst surface versus if I put 10 weight% platinum on my catalyst surface, they're going to have very different active site densities. And so what we're defining as active site density is just how many moles of active site do you have per unit catalyst mass. And the reason that's important is so that we can compare catalysts not on a mass normalized basis, but on an active site normalized basis. So we have this concept here of turnover frequency, as you can see here in the figure on the left, which describes essentially the frequency at which this catalytic cycle happens, or essentially how many of these turnovers do we have happening per unit time. And so you can numerically calculate that by taking your mass normalized rate and then further normalizing that by the active site density. And so what that'll tell you is this is how many turnovers you have per unit time. So dimensionally it's a frequency, but in terms of units you've got moles of product forming per mole of active site per unit time. And so given that this is how we really want to compare catalysts based on this turnover frequency, it's critical that we be able to determine the active site density. And so that's where catalyst characterization comes in. Because as I was just describing in terms of how, for example, supported metal catalyst works, we have these length scales of catalysis, where on the micron level we might see all these porous networks, and if we zoom in a little closer, we've got within a single pore channel, we start to see some of these metal clumps. And then if we look even closer now on the nanometer level, we'll see these supported metal nanoparticle structures that are essentially our active sites. And taking a closer look at what's happening there, so if we have a supported metal nanoparticle, say about 2 nanometers in diameter, we're going to have these cluster of atoms forming something that's almost a hemisphere as an approximation. But what really matters is not all of the metal atoms that are deposited on the surface. It's really more the exposed metal atoms shown here in gray. Those are the catalytic surfaces that are available for reaction, that atoms that are diffusing from the bulk phase can then access, absorb onto the surface, react and form the product, and then finally the product can desorb. So what really matters here in terms of numerical value is this quantity dispersion, which essentially is the fraction of exposed metal atoms to that of the total number of atoms you have in the system. So the higher dispersion, the more effective you're using your metal catalyst. Because again, the atoms stuck in the bulk are not going to really be participating in any catalytic cycles. Now they do have some effects, and we'll get into those later in the presentation. What we can also then determine and relate between dispersion is the average particle diameter. And so just from geometry, what you'll eventually see is that the particle diameter of these supported metal nanoparticles is going to be inversely proportional to the dispersion. So the bigger your nanoparticle, the less dispersed it is. And that's mostly just because your surface area scales with the square of your diameter, but the volume squares more with the cube of your diameter. And then we have also these terms which you can get from handbooks, the bulk volume for your metal atom and your atomic cross-sectional area. So how do we actually characterize it? How do we actually figure out your dispersion, or what the metal surface area that's available for catalysis? One technique is carbon monoxide chemisorption, and that just comes from the fact that carbon monoxide will strongly bind to metal nanoparticles. So if you think of something like the catalytic converter in your car, one of the big problems they face there is if carbon monoxide that's coming out of the engine sticks to your catalytic converter, which is just a supported metal catalyst, it will poison it, and then you will no longer be meeting emission standards. But back to carbon monoxide chemisorption, so what we can do is dose in known amounts of carbon monoxide, and as you'll see in the figure on the right, you'll get an uptake curve or an isotherm. However, there the carbon monoxide is sticking to both your metal and your support material, but on your metal it is strongly binding. So then you can then remove the carbon monoxide that was bound to the surface, since it's just physisorb, and repeat the same isotherm. And so what you'll get this time is just what's been reversibly absorbed or stuck to the support material. And so when you take the difference of those two isotherms, you get your irreversibly bound carbon monoxide, or those that were stuck to your metal sites. And from that, then you can correlate that and quantify how many active sites you had exposed of this metal. A more direct method is to use electron microscopy. So if you think of transmission electron microscopy, you can get nanometer scale resolution, take a look directly at these nanoparticles. So here I'm showing you a supported ruthenium nanoparticle on a silica surface. You'll get some normal distribution, about an average, as you can see from the histogram and the inset. And what we're looking at directly are these, again, these hemispheres of supported metal nanoparticles. And then just from the images, we can, using image processing software, you can get an average particle size, and you can get a standard deviation, and then correlate these back to activity or compare them to results that you would get from, say, carbon monoxide chemisorption. Now, switching gears a little over to something like solid acid catalysts, where some of the most famous examples are zeolite materials, where essentially you have a silicon framework, such as the case here with this MFI framework that was developed by Mobile. And into that you can incorporate into certain locations aluminum atoms, and what this creates is a charge imbalance, which can then be corrected by placing a proton, and that's what generates your Bronsted acid site. And so what happens here is you've created a catalytically active site, and it's Bronsted acidic. Alternatively, if your aluminum is not incorporated into the framework, but simply deposited elsewhere, or extra framework aluminum, that can generate Lewis acidity. And so one technique to try and characterize these solid acid catalysts is to use infrared spectroscopy, or specifically here we would be using Fourier transform infrared spectroscopy, or FTIR, where what you would basically do is you take a vacuum cell, inside of which you can see in the cartoon on the right, you press a self-supporting wafer of your catalyst. It's placed in a sample holder which can be heated and controlled. and then you can pump down this chamber under vacuum, and it's placed in a perpendicular fashion to the IR beam. So that comes out from your IR source, and that goes to a detector. And from there, you get a spectra that's on the infrared range, and from there, you can tell a lot about what's going on the catalyst surface. Now, what we sometimes do and combine with this technique is to use a basic titrate. So again, these are solid acid catalysts, so we want something that will strongly interact with them. And so using a basic molecule like pyridine, which will have strong acid-base interactions, we can see two different types of acidity on a solid acid catalyst surface. If the pyridine was to adsorb on a Bronsted acid site, you have a proton transfer happening. The Bronsted acid is just a proton site. It gives up that proton, and you form this pyridinium ion, which has a very characteristic wavelength or wave number of 1544 centimeters inverse. Now, if you had, say, extra framework aluminum or Lewis acidity, you would then have this lone pair interaction from the pyridine with the Lewis acid site, and you get this characteristic vibrational frequency again at 1454 centimeters inverse. So this is a nice qualitative way to distinguish whether you have Bronsted or Lewis acidity, but then using a concept like Beer-Lambert's law, we can further extend this to correlate the area we get underneath these peaks at the characteristic vibrational frequencies, and with the use of certain molar extinction coefficients, we can then correlate this back to an active site density. And so then we can determine how many Bronsted acid sites do we have and how many Lewis acid sites do we have. Alternatively, another technique which doesn't rely on spectroscopy is alkylamine decomposition, where if we have a Bronsted acid site shown here as would be in an aluminosilicate material case, we can then adsorb a primary alkylamine, and you have this proton transfer happening. And what's characteristic of alkylamines reacting on Bronsted acid sites is they will undergo this Hofmann elimination reaction, and you form an alkene product and a resultant ammonia product. Now, this is an interesting way to characterize solid acids because this reaction will happen exclusively on a Bronsted acid. On a Lewis acid, the alkylamine will adsorb, but it will then desorb intact. So this is, again, another way we can differentiate between the different kinds of active sites. We can also then go further and quantify. So on the right here, I'm showing you what would happen if you were to saturate the catalyst surface with these primary alkylamines and then ramp up the temperature. And so you get propene evolving. And so if you assume that for every propene molecule you see, you had a Bronsted acid site, we can then quantify and determine a Bronsted acid site density through this Hofmann elimination reaction. And finally, what's also important and more universal in terms of different kinds of solid catalysts is knowing what the surface area of the catalyst is. Mostly what we're dealing here are porous materials, which can be divided into three different types. We can have macroporous materials, so if you think of something like magnesium oxide, it's got a pore diameter that's going to be bigger than about 50 nanometers, so not so much porosity. However, mesoporous materials, such as amorphous silicon dioxide, you'll have a pore diameter that's anywhere between 2 and 50 nanometers. And then we come to these microporous materials, such as zeolites, which have less than 2 nanometers in pore diameter. And so how we characterize this is with gas adsorption techniques, where we can take something like argon, and as you can see in the figure on the left, we keep successively dosing more and more of the gas, and we can use sensitive pressure transducers to measure how much has been absorbed onto the surface. And at different parts of this absorption will have characteristic behavior that evolves, which is illustrated in the figure on the bottom right, where depending on the relative pressure you're at of your adsorbent gas, you'll see different isotherms that evolve. And so, for example, if you see this type 1 behavior, that's pretty characteristic of a microporous material, where once you're beyond the monolayer, you don't really have much else happening. But then more of these non-porous and mesoporous materials, you can have more than monolayer behavior happening. You can have this multi-layer behavior happening, and so you get these different shapes. And so from these techniques, we can learn a lot about the surface area of the materials we're dealing with, the average pore diameters, and what kind of material in terms of the pore structure are we expecting. And so that brings us to the end of part 2. I guess at this point we'll take a pause and take some questions.
All right, part 3. So part 3, we're going to cover what we call more advanced introductory concepts in heterogeneous catalysis. And I think the most common question people ask is, what makes a good catalyst? So if I'm thinking of a reaction, all these different metal options, different acids, and all the opportunities in between in structure, etc. So there's no good answer for this, but there are some guiding principles. I think the most famous one is Sabatier's principle, which is the interactions between the catalyst must be, quote, just right, and neither too strong nor too weak. And you can see that if you think about a very simplistic reaction concept that's drawn in the top left. If you have A2, a diatomic that has to adsorb dissociatively to form 2A, that could then react on a surface to make 2B, and then that could desorb as B species. And you can kind of imagine a continuum of different catalysts with different binding strengths. If you bind A really poorly, you're going to adsorb and dissociate very poorly. So at any time, you're going to have a very small amount of A on your surface. We'd say it's a slow adsorption, slow dissociation catalyst. As you get stronger and stronger binding, though, what will eventually happen is you'll very readily dissociate A, but then you'll adsorb B very strongly, and you'll end up with a lot of B on your surface that won't come off, in which case you're kind of gone too far. So what you really want is a catalyst that binds strong enough to dissociate and adsorb A, but not so strong that you can't remove B. And this concept of Sabatier's principle has been shown over and over and over. And here's a good example of it. This is formic acid decomposition, where we start with formic acid in the gas phase. It adsorbs, decomposes to carbon monoxide and hydrogen, and then that can decompose or desorb from the surface. And what you see on the right is the temperature of fixed rate of reaction as a function of the heat of formation for these different metal species. And what you can see is that you see this, it's also called the Sabatier curve or a volcano peak or a volcano curve. It goes by a couple different names. But very clearly that balance of dissociation and desorption is matched very nicely for species like platinum, iridium, and ruthenium. But species like silver and gold on the left, or nickel, cobalt, and iron, either bind too strongly or too weakly to be near the optimum reaction rate. Now that's a very simplistic kind of interpretation, but it shows up in many different systems, including some very important ones. Right now there's a huge focus on making ammonia both as an energy storage material for storing hydrogen and energy, but also for fertilizer and many other applications. And so there's a big effort now to see, can we enhance the rate of reaction to synthesize ammonia. Now what's interesting about ammonia is it's been studied with heterogeneous catalysts for over 100 years, and there's a lot known about its chemistry. And what we've come to the conclusion, if you look on the left, is that if you take N2 and H2, you will adsorb it and dissociate it to low energy. It'll eventually then go through a series of steps to form NH3, which then has to desorb. So it fits very nicely with this cartoon idea I showed you 2 slides ago. And it turns out that this Sabatier principle is overwhelming in its effect in the different types of metals. If you look on the right, as you work at any interesting composition of NH3, 1% to 10%, you can see that there's a very clear Sabatier peak, with the best materials being iron, ruthenium, and osmium, which is what's found experimentally. And if you look, that's a log plot of the turnover frequency. So the big question in research, and this is a frontier research question, is how could I make a material that has the binding sites I need for adsorption and dissociation, but also then has the right binding sites for desorption? And then you'll hear catalysis scientists talk about this constantly, which is how can we get off the Sabatier curve? And this question goes on, looking for an advanced strategy right now. Now there's other issues with thinking about different catalytic materials. If we think about supported metal clusters, for example, these form different structures depending on the size, and in any particular metal, you have different sites. You have corner sites, plane sites, edge sites, etc. And smaller particles tend to have a higher fraction of these low coordination sites. So not only do you benefit from dispersion, but for some species, such as gold, they only become active when you get sufficiently small and you have a number of low coordination sites. That's very important for particularly some metals. You can think of this exact same issue only in the reverse case where you have a high metal loading, and rather than in particles now you have kind of a continuous metal surface, but on that metal surface you have steps, you have kink atoms, you have step vacancies, etc. You can have single atoms that are separated out in different places. Each one of these sites on a metal surface will have different activity because the coordination will be different with the substrate. Now, because of that, you can almost say that this problem seems a little bit hopeless in the sense that you have all these different sites that can even change with time. How do you deal with this? Well, there are some classic examples where we allow the metal to form all the different types of sites that we want, and then we can actually try and suppress the sites that are negative for the chemistry of what we're trying to achieve. And the classic example of this is ethylene epoxidation. If you look on the right, if you take ethylene and react it with oxygen, it can form ethylene oxide, a very useful chemical for a variety of applications. And that epoxidation chemistry happens in competition with complete combustion to make CO2 and water. And it was discovered a couple of decades ago that if you add chlorine into this reaction, you co-feed chlorine, what it will do is it'll bind to the sites that preferentially form combustion products, and your selectivity to ethylene oxide will go up substantially, tens of % for ethylene oxide. So let me just kind of give a bigger picture approach here. What we're really talking about now is you can go through different synthetic techniques to make an active site, whether it be a supported cluster of metals or an acid site or bimetallics, etc. But then there's all these other effects that come in that complicate this. For example, the support interacts with the metal in a way that can have electronic effects. Or, as I was just saying on the previous slide, you can use promoters of different types that will selectively bind to sites that are a problem for your chemistry. But there are many other things you can do to alter the chemistry on the active site beyond just making the active site the way you want. For example, you can introduce solvents, which can change the energy of the adsorbed species, but also the energy of the transition states. Or you can encase these in different porous materials, which can have a variety of electronic and steric effects on the chemistry you're going for. So I'm going to turn this over to Omar here to complete this section.
All right, so one of the first concepts I wanted to discuss in this thought of beyond the active site, or more looking at the reaction environment in this case, is solvent effects and heterogeneous catalysis. Now, they're a bit more of a mystery than in homogeneous catalysis, where I believe there's a much better handle on what's happening there. But with heterogeneous catalysis, one aspect to consider is when you have a solvent environment, that solvent is going to interact with the catalytic surface. So some of these solvent molecules will then also adsorb onto your active sites. Now, more than just interacting with the catalytic surface, you can have adsorbate-adsorbate interactions. So a solvent absorbed on the surface can then interact with an absorbed reactant or product species. And one example that we commonly see of this is hydrogen bonding, where water will adsorb on a catalyst surface. It will form hydrogen bonded networks on the catalyst surface. And then if it can interact with, say, a transition state on the surface that can participate in hydrogen bonding, it can then lower the energy of that transition state. Now, where it gets interesting is if the solvent can preferentially stabilize the transition state or lower the energy of the transition state more so than it would the energy of the reactant state, for example. And so what that would lead to is a reduced activation energy or barrier for that kinetically relevant step, shown here with the red bar being smaller than the black bar. And so what this will lead to is an enhanced rate of reaction in the presence of a solvent that can do this. Now, if you expand this even further, let's say you had a desired reaction and an undesired reaction. And we commonly see this in biomass catalysis, for example, where we have acid-catalyzed dehydrations. You have a desired dehydration pathway and you have an undesired pathway where you just get polymerization of products to very heterogeneous products. Now, some solvents then, not only do they enhance the rate of the desired dehydration pathway, but they also destabilize the undesired reaction pathways. And so what that does is it improves the selectivity to your desired pathway through kinetics. So solvents can play quite a big role in terms of how to affect your catalyst site. Now, another concept in terms of beyond just the active site is the support material on which the active site sits. Up until this point, we've just been talking about the support as just an inert material, which is a high surface area material that you disperse your active site onto. But for example, here in the case of a platinum catalyst, what's been shown by Van Ice is when you take a supported platinum catalyst, whether it's in the bulk, just as the platinum case here on the figure all the way on the left, or if you put it on a silica support, alumina support, you get some differences, but nothing too major. But when you put it on a titanium support and you reduce the whole catalyst at high temperatures, or essentially heat it up to about 500 Celsius in hydrogen, you get some very interesting effects where you see this orders of magnitude jump in the reactivity for acetone hydrogenation to isopropanol. And what's been reported on for quite some time in catalysis are these strong metal support interactions. So the metal is now not just sitting on the support material and it's a dispersant, it's interacting with it, and the support material can affect the electronic structure of the metal atoms in close proximity to it, especially what are called these interficial sites, or the atoms that are in direct contact with the support material. One way that's thought of happening is you have with titanium, it's a reducible oxide support. So silicon dioxide or aluminum, unless you heat them up to really high temperatures, they're not going to change their oxidation states. But titanium here, that can readily happen at about 400 or 500 Celsius. And so changing that oxidation state of the support material can lead to really interesting effects and promote the rate of reaction on a per active site basis. Another concept in terms of how we can tune selectivity through kinetics rather than just changing the solvent environment or changing the support material comes down to these cavities in which we place the active site. And this was made famous by ZSM5 catalysts, which have these MFI frameworks. And what's unique about them is you have this industrially relevant chemistry where you have toluene and it's going to undergo alkylation with methanol, and you hopefully want to make paraxylene. Now the problem is these reactions happen very quickly, and if you let it go to equilibrium, you're not going to get all that great of a selectivity towards paraxylene. Now what you can do with these zeolite structures, which have very well tuned pore sizes that are again microporous, so less than about 2 nanometers. In this case here with ZSM5, you're talking something about 5.5 angstroms. The reactants can diffuse into the pores where the active sites are located, undergo the reaction, and form all the different ortho, meta, and paraxylenes. However, paraxylene can diffuse due to its shape relative to that of the pores. It can diffuse orders of magnitude faster than ortho and metaxylene. So what will happen is they will keep interconverting in these catalyst pores, but it's really the paraxylene that's going to have a good chance of getting back out of the pore. And so that affords you high selectivities to paraxylene, where if you use, say, a mesoporous material where all of the products diffuse out at roughly the same rate, you're probably going to hit that equilibrium wall set by thermodynamics. So again, shape selectivity can really be interesting if you can tune it, your pore sizes relative to that of both your reactants and your products. And up until this point, we've been discussing one kind of active site. However, there's a lot of work that's been going on in catalysis with process intensification. When you talk about realistic processes where you want to go through multiple reaction steps, and sometimes those different reaction steps are going to need different kinds of active sites. Now, the brute force method is just to have different reactors for each of those steps. However, that costs a lot of money. And what you can do if you can design a catalyst in such a way is place multiple catalytic functionalities or multiple types of active sites that suit your needs. So one example that's been developed here at the Center for Sustainable Polymers is this technology of going from itaconic acid, which you can derive from glucose through enzymatic technologies, all the way to isoprene, which is a renewable diene monomer that you can then form a lot of interesting polymers out of. So here there's several steps along the way to get from itaconic acid towards isoprene. And to complicate matters even further, you have both liquid phase reactions and vapor phase reactions that are going to occur. So what was done here was to develop a hydrogenation metal catalyst, because that's part of the functionality that's needed, as well as something that has acid capabilities, because you're also going to have dehydration needs to form your isoprene. And zooming in on one of these steps to give an example of that, or in a sense, this rational catalyst design approach, are these bimetallic catalysts that you can form. Again, we don't only have to form one catalyst, as Paul was talking about earlier with the Sabatier principle. You can try to form bimetallics to get in between the different points you have on that curve. So here was a specific step that was a kinetic bottleneck in the itaconic acid to isoprene technology, which was turning this lactone, methyl gamma butyrolactone, into methyl butane diol. So you have to open up the ring and add in some hydrogen to get to your diol product. When palladium catalysts were first considered, as those were working for all the subsequent steps, it seemed that there was quite a low rate for this reaction. Now, rhenium is known as an oxophilic promoter, so when you make bimetallic catalysts with, say, group 8 noble metals like palladium, you can really enhance the rate of a reaction, and particularly true for these lactone hydrogenation chemistries. So what you see here is as you keep adding in more rhenium going from left to right, you can see the rate of reaction increasing. And what's possibly happening there is rhenium is oxophilic, and it has much better catalytic capability as splitting open that carbon-oxygen bond and opening up the ring and letting the palladium do its hydrogenation job. However, there's an optimal. As you keep adding in more and more rhenium, you will drop the rate of your reaction, and that is likely due to the fact that as you put in more rhenium, you're getting rid of the palladium that you still need to perform the hydrogenation. And so you see this optimal balance that exists somewhere about 20 mole% rhenium. So again, this is another example of where we can take multiple types of active sites, not necessarily physically separated, but they're different in the types of catalytic activities that they provide. And so coming to this part here, we'll continue straight on, and we'll have questions at the end of this section. Just going on to more realistic catalyst systems and what you might face there. So what I'm showing here is a cartoon of catalyst deactivation mechanisms. So in academia, we like to focus a lot on what a catalyst can do and trying to understand it, but in practice, a big problem that can be faced is the deactivation of this catalyst, or how stable is this catalyst. You put it on stream, it's good in the first hour, but many of these catalytic reactors need to stay online for days, weeks, and months without regeneration or replacement. So some of the issues you might face are poisoning, where let's say you have a contaminant that likes your active site very much, and it will bind there very strongly and not allow any other reactants to absorb. You can have leaching happening, which is a particular problem in condensed phase chemistries. You're running a metal catalyst in water. Some of the metal atoms would prefer to be in solution thermodynamically, and they just leave your catalyst surface and therefore leave your reactor system. Sintering is another one which I'll get into, which is essentially the agglomeration of some of your metal nanoparticles, and that leads to a decrease in your active surface area. Fouling, or a particular example of that is catalyst coking. We also have attrition, where the catalyst particle itself can start to break due to mechanical stresses, especially in a pressurized system or a fluidized bed system, and parts of your catalyst will break off and leave your reactor system. So looking at the case of poisoning, especially with these sulfur compounds, when you think of a metal catalyst like ruthenium and you're trying to perform this furan hydrogenation, for example, if you have something like sulfuric acid around in solution, a lot of these sulfur species will very strongly bind to the ruthenium surface and not allow any other reactants to absorb and undergo a catalytic cycle. So some of these poisons can be a serious issue and can very quickly destroy a reactor system. coming to the idea of catalyst sintering or particle agglomeration, what can happen is, let's say you have two of these supported metal nanoparticles. They can be mobile on these support surfaces, especially at elevated temperatures. They can start to move around. Alternatively, atoms can break off from the clusters and travel along the surface and go to another metal nanoparticle. And what this eventually leads to is the growth of your metal nanoparticle. And so in this case here in the cartoon, you have two nanoparticles, they grow into one larger one. So what's the problem with that? Well, the problem is, if you look at the geometry of this, the particle diameter is inversely proportional to the dispersion, which again is the fraction of exposed metal atoms to that of the total amount of metal atoms available. So what this means is, as you make your particle diameter bigger, the moles of metal atoms exposed on the surface that are responsible for catalysis is going to decrease. And so what can happen under realistic conditions, here I'm showing you micrographs, TEM micrographs, of a ruthenium on silica catalyst that was employed in an aqueous phase hydrogenation. On the left, before you go into the reactor, you have a nice homogeneously dispersed system, homogeneous distribution around your average. But coming back out of the reactor, you see some of these really big nanoparticles that are forming. And you can see in the histogram as well, you have this large tail to the right. You no longer have this nice Gaussian distribution, all of which is very characteristic of catalyst sintering. So what had happened here is that the nanoparticles become mobile, they find each other, and this is a thermodynamically driven process, unfortunately, and you will lose surface area. And what occurs in terms of catalytic activity, here on the figure on the extreme right, you see your catalytic activity decreasing with time, and that's due to the loss of metal surface area due to the nanoparticles sintering. Another common example faced in terms of catalyst deactivation is when you deposit what's colloquially known as coke, or essentially these are carbonaceous deposits that come from your reactants in the first place and form on the metal surface or in an acid catalyst and block it from further reaction. So one common example in the case of alkane dehydrogenation, you take something like propane, you want to turn it into propylene. What can happen is you have these side reactions, but they don't complete a catalytic cycle. For example, you would get a deeply dehydrogenated species that is very strongly bound to the metal surface, and it doesn't complete the cycle by desorbing, and so it blocks the active site from participating in any subsequent reactions. You do have solutions for this where you can subject the catalyst to a high temperature treatment, either in air or hydrogen, depending on the catalyst you're employing, and that will usually get rid of most of your coke formation. However, you can have some very heavy coke or hard coke forming, which are really graphitic species that are not easy to get rid of. And so at this point, I'll turn it back over to Paul.
Sure, and to finish this up, we can start to think about, if we have a catalyst, how do we take it into a real reactor system? And that is that most of these industrial reactors are packed tubes of catalyst pellets or they're fluid beds, which means we usually in the laboratory will think of these as just systems that are controlled by chemistry, but in reality most catalytic reactors are controlled not only by chemistry but by other transport phenomena such as heat transfer, diffusion, or momentum transfer. And a classic example of this is the reactor you see on the left. This is a methane steam reformer to make hydrogen from natural gas. And in this system, you take steam and you react it with methane over a supported metal catalyst and make hydrogen and CO. That's an endothermic reaction, and that happens within these reformer tubes, which are packed with catalyst. On the outside, you'll actually burn methane and generate heat, which can be conducted then through the tube into your catalyst to drive their overall reaction. So in terms of the reaction rate, we might determine the chemical kinetics, but it might ultimately have control resulting from some other rate limitation. Now this extends to all sorts of different systems. The system I was just talking about, you can see pictured on the left, and you can actually see in that picture down here on the bottom next to the logo, that's just a little person. So these are enormously large reaction systems and it's not hard to believe that all other transport phenomena could be introduced and complicate the actual system. There's anything from the large scale you see on the right all the way down to something like the catalytic converter on your car, the three-way catalytic converter, which can do multiple chemistries on supported metal catalysts. And this now, the emerging area is in making 3D printed microreactors, which you see on the far right. That's smaller than your thumb, small reactor with multiple catalytic channels. So to put this together, I think one of the complexities with heterogeneous catalysis is that it has an immense number of skills you need to do to solve any one problem. We haven't talked much about it, but you can imagine all the synthesis techniques that are introduced to make all these different materials the way that you want and to optimize for your application has to be combined with characterization to know what you've made and exactly how it works. The chemical mechanisms that will be determined ultimately dictate the selectivity of your chemistry and how fast it's going to happen, and that has to be characterized with tools developed specifically for the kinetics. The thing that's changed in heterogeneous catalysis in the past 15 years in particular is the ability to do computational chemistry on large heterogeneous materials. That's changed our understanding of a lot of the different chemistries. And combining the kinetics with the computational chemistry with spectroscopy now gives us a very good insight of what's on a surface, what controls the chemistry, and how we can make it better. Now, ultimately, all this gets wrapped together in engineering and modeling of reactor systems to relate all of the chemistry with an actual catalytic reactor. So putting that together for somebody like a catalytic reaction engineer means that you usually need to partner, and you end up as a very interdisciplinary field of research. So I think that covers a lot of topics related to kind of what I would say is the basic ideas of heterogeneous catalysis, but this is an entire field. And you can start anywhere from the very far right, which will have introductory concepts in kinetics and catalytic chemistry, all the way to the far left, and books written by University of Minnesota professor Matt Newrock that cover really advanced concepts in molecular heterogeneous catalysis. So thank you for your time.